Hello, everyone. Thank you for joining us today. I'm CON308-S. I lead solution architecture for Spotist in the Americas. With me are Tim and Jesus from Ticketmaster. Introduce yourselves.
Yeah. Tim Nichols. I run the technology platform team at Ticketmaster. So we'll learn a little bit more about what we do in a little bit.
Hi, Jesus Carrillo, systems engineer at the Kubernetes team at Ticketmaster.
Awesome. Thank you for joining us, guys.
We're going to take a seat over here.
So as I mentioned, I'm Tom from Spotist. Spotist is the continuous cloud optimization platform. Kind of from a paradigm where you do CI/CD to all your deployments and all your code, we believe we should also continuously optimize the infrastructure underneath. Generally, in a nutshell, we automate cloud workloads to improve performance, reduce complexity, and lower your infrastructure costs by up to 90% by both efficiently leveraging the infrastructure and leveraging different pricing models inside AWS. A little bit about us. We were founded in 2015. We've raised $52 million to date from Intel Capital and Highland Capital. And today we have 5 offices globally with over 170 employees and 1,000 customers. Since we started focusing about Spot instances in our early days, we've today turned into a one-stop spot for cloud optimization. And everyone, don't worry, I'm going to finish with the marketing stuff in a minute. We have the Cloud Analyzer platform, which starts from your cost and usage report, and then helps you start drilling down into every cluster, every workload, and every system in your environment to figure out what steps you should take to optimize it, and then also take the steps for you. If that means bin packing it more efficiently, if that means using different instance lifecycle types and sizes, and using our different tools to do that. Aerco does continuous cloud commitment management, managing both your savings plans, your RIs, converting them in real time, changing what you need, and making sure you don't have any waste. Ocean, which is what we want to talk about today around the world, is the notion of serverless containers and how do you achieve a Kubernetes cluster that you don't really need to manage the instances underneath. Elastic was our core product around web apps and auto-scaling, anything on Spot instances, and manage instance, the ability to run a Spot as a stateful workload while preserving its IPs and single instance workloads. Our strength is in our numbers. We manage over 3 billion cloud resource hours per month, helping our customers save 60 to 90% cost reduction from their EC2 bill, saving them hundreds of millions of dollars yearly. We work with worldwide in over 50 countries, serving enterprises, small, medium businesses, high-growth startups, tech unicorns, and Fortune 100 companies. Now that my marketing team is happy, today we want to talk about the 3 layers of optimizing container infrastructure. Really, when you run containers today, you work in 3 different layers. Your instance sizing, are you using a C2, a C5.2XL, an M5XL, a P3 for your GPUs? Are you using one of them, or are you using all of them? And how are you optimizing across? The pricing model, as you all know, AWS has several pricing models. The on-demand, which we're all familiar with and start with, paying the full price per second for what we use. The reservations, where you commit upfront to specific instance types and keep using them for 1 to 3 years and get a certain discount. Most recently, the savings plans, both for EC2 and compute, that work across your environment. One of the lesser-known pricing models is the Spot instances, AWS's excess capacity, and how you leverage it. After we dealt with which instance size we're using, how we're paying for it, we also need to focus on what is our container requesting. We can optimize infrastructure as much as we want, but if every developer gets to ask 5 times the resources his application actually needs, it's all pointless because we're paying 5 times of what we're actually running. And today, we want to talk about what are serverless containers. First, just to level set the room, there's like a quick overview of the anatomy of Kubernetes, which is the container orchestrator we want to be talking about today. Kubernetes has 2 main pieces. One is the control plane, which is basically your Kubernetes masters. If you're using a COPS, a kube spray, a kube ADM, you probably have 3 of them distributed across 3 availability zones to maintain their high availability. If you're using AWS's EKS, then AWS manages that for you while maintaining your SLA and all the availability you need. Then you have your kubelets or your node agents, where your workers and your actual services are running. And then you have your services themselves, which is what you're all working so hard to build and deliver to your customers. Today we want to focus mostly about your nodes, your worker nodes, where the majority of the cost, the majority of the overhead in Kubernetes is, with services like EKS taking all the management of the control plane away from you. It's become really simple nowadays. So we'll focus on the workers. And why are they challenging, really? The main reason for that is that you're scaling on two different levels. Ticketmaster will soon share with us. You have a massive engineering organization. You have hundreds of developers. They're all building applications, services. Each one of them scales for different reasons, by a CPU, by memory thresholds, by number of requests, by number of people trying to approach this pod. At the same time, you try to do something that's relatively cloud native, and you put an auto-scaling group underneath. You give it a scaling policy. It has maybe one, maybe two instance types in it. And there's a single scaling policy that tries to match your infrastructure to your application. And as your application layer grows and grows and grows, you keep kind of the infrastructure the same, and it becomes highly inefficient. It doesn't scale on time. It doesn't respond the way you want it to. It's just too expensive. As I mentioned, the top layer is usually affected by the horizontal pod autoscaler of Kubernetes. Every 30 seconds, it looks at the metrics of your deployment. It updates the replica count, increases the deployment size to make sure you have more of your application to serve the requests. And then it will cool down for 3 to 5 minutes before taking another event. Now, what problem does that cause us? Because we have such a dynamic infrastructure, we have dozens, if not hundreds of applications scaling up and down all day long. We need to meet our application demands. But at the same time, we don't want to cause too much waste. We don't want to just spin up resources. The easiest way to do that is just spin up 3 times the infrastructure of what you might need. Always keep it up there. Always keep it on. Pay for it per second. Your application will always be there. But the problem is that you actually want to minimize your idle resources. You want to optimize your workloads. You want to make sense of what you're using in the cloud. And with that, we're back to our original problem. We have 3 layers that we need to optimize: our instance sizing, our instance lifecycle, and our pod right sizing. So let's dig deeper into each one of them. The instance sizing layer. So as I mentioned, the traditional method was, let's just scale our infrastructure when all of our EC2 instances reach a certain threshold. We're at 70% CPU. Let's add 5 more instances, cool down for 5 to 10 minutes, hope they can catch all the replicas from our 100 different services, and just pray that it's going to keep working. In reality, it's not. You're going to have to constantly adapt it, and tomorrow one of your developers will go and increase his replica count from 10 to 1,000 because your application is blowing up, and your auto-scaling group will take 5 hours to scale up, and everyone's going to give up on your product by then. So you need to be much more responsive. You need to be much more adaptive and much more agile about how you manage that. And that's why people go with a bit of a Tetris scaling. So you choose a few instance types, you use a cluster autoscaler, and you spin up more types of instances as your containers are coming in. But this also has some challenges with it. For example, let's imagine you have this pod coming in. It requests 3 vCPUs and 4 gigabytes of RAM. Can't see everything on the slides. But for the sake of the argument here, it's somehow lost the top layer there. We have a C3 large, we have a C3 2XL, and an M3 medium. You have some space on the C3 large. You have some space on the C3 2 extra large. And then you have this pod coming in. In reality, between the two of them, they could host that pod. But the pod can't split itself in half. So neither of them can actually accept it right now. You scale up, and you accidentally scaled up an M3 medium. You still can't handle that pod. It's stuck in a pending state. You manually go and add another node into the cluster and solve that and do that every hour. Again, you might, well, we're losing one layer here, so I'll skip this slide. But even when you scale down, the same challenge can happen. In reality, you have enough place to scale down your largest node in your cluster. But if you take the pods away from it, again, not one given instance in your cluster can handle that pod right now. So you're stuck, and again, you have to go and manually intervene. That's why Tetris scaling is sometimes hard. It's very confusing what to scale when and how. And with that, we believe there's a better way, and that's container-driven scaling. Stop thinking about the nodes. Stop managing them. Don't really bother with what you have there. Stop planning your infrastructure a year before you build applications on it. We want to live in a world where containers are the first-class citizens of our clusters. Essentially, every instance size, type, and lifecycle will be determined based on the pod that's coming into it, its requirements, while honoring all of its labels, stains, tolerations, persistent volume claims, affinities and anti-affinities, and any other config you have on that pod should be respected by the infrastructure, right-sizing it as you go in real time. So that means you get a small pod, maybe an M3 medium can handle it. You get a larger pod, it's time to spin up a C4-2XL. You get 2 medium pods, you spin up a C5XL. One of your data scientists decide to do something with image rendering, so he needs a GPU work. Again, in a traditional model, they would have to go back to the DevOps engineer saying, hey, can you also spin up some GPU instances in that cluster? You have to go, you have to plan for them, you have to connect them to the cluster. You're wasting everyone's time. So what you want to do, again, the pod is requesting a GPU, spin up a GPU instance. And if the pod by no means can handle any type of ephemeral instances, it can also ask for an on-demand and get it spun up at the same time. Now, so sounds great, but it's obviously a lot of overhead, so why should we bother? And let's look at some numbers. So let's say you have a pod, 6.5 gigs of memory and 1.5 vCPUs. And you put it on an M5 large, it's fairly well utilized. You get 82% memory utilization and 75% CPU utilization. But you can only put one of them on that instance, which means that pod costs you the entire instance cost, or about 9.6 cents an hour to run it. So you go one instance size up. So you're paying twice the price, and you can put 2 pods. So you're essentially still paying 9.6 cents an hour for that pod. If you go another instance size up, you're paying twice as much, but you can put 2.5 times the workloads on it. So suddenly, you're only paying 7.7 cents an hour per pod. You're utilizing your instance at 98.5% for memory and 94% for CPU. And essentially, you're reducing the cost of running this workload by 20% simply by choosing a slightly larger instance that can more efficiently bin-pack the pods on it. So we get a different scenario. We want to switch the instance families. So we started our cluster. We spun up a pod. The cheapest way to handle a 6.5 gigabytes of memory and 1.8 vCPUs right now is a C5XL. We get 82% memory utilization. It's slightly cheaper than the M5. But we're only at 45% CPU, which means we kind of have a lot of idle CPU there, but we have no memory to actually take a new pod. So we're paying about 17 cents an hour for the pod. We switch it up to an M family. We have twice the memory. So instead of being stuck at 45% CPU, the very same instance that only costs about 6% more can take twice the workload. Now we have still 82% memory reservation, just like we did at the C family, but our CPU goes up to 90. And with that, we're dropping the cost per hour per pod to 9.6 cents again, or 43% cheaper by simply switching up your instance types. Now again, when you do that at scale, it becomes more and more complex, and that's why we care about pod-driven auto-scaling. You need to make hundreds of these decisions every day and every workload in every scaling event. And that's why you really want to do that in a very dynamic, autonomous way. What does this mean for you? What are you actually going to be getting from that? So you won't have to manage any of your underlying infrastructure. You will scale by requests based on real-time requirements. You will only be paying for what you're using, so you're eliminating all the waste, and you're constantly bin-packing the cluster according to how the pods are working. You can scale it down to 0, because if there are no pods, why keep the cluster running? If it's a dev cluster and you're just scaling down the replicas at night, you should also scale down the instances without having to take an extra step. And you get much faster scaling because it's much more responsive to what your application actually needs. So this is really why we should care about using mixed instance types when we run containers. We have a multi-tenant cluster with a lot of different applications. Each one of them should get what works best for that application, and not what's easiest to decide when we set the cluster up on the first day. From here, we'll go to the instance pricing layer. So we chose the right instances at the right time. Now, how do we want to pay for them? As I mentioned earlier, option number 1, the easiest, pay on demand for what you go. Still, by switching the types and sizes, you can save a lot of money, even on your on-demand machines. Option number 2, which also makes a lot of sense, but only for baseline capacity, because again, we have a highly dynamic infrastructure. We can only commit and reserve what we run at the base of it, and whatever we spike on, we would lose all the savings if we're not using it 24/7. So reservations, savings plans are really good for the baseline capacity of our Kubernetes clusters. But as I mentioned earlier, AWS has another pricing model that's less familiar, and that's the EC2 spot instances. Spot instances are essentially the excess capacity inside the AWS cloud. For any of you who manage the data center, you know it's essentially impossible to run it at over 60–70% utilization on average. There's always going to be some excess capacity inside of it, which you're paying for the real estate, you paid for the hardware, you're paying for electricity and maintenance. And what AWS has done about it is create an excess capacity market. All instance types and sizes you're familiar with today, at 60–90% discount from the on-demand price, charged per second with no commitments at all. That sounds great. But because it's excess capacity, it can also run out. And when it runs out, AWS will give you a 2-minute notification and terminate your cluster. But if you have ephemeral workloads that can handle these things very gracefully and can be properly managed around it, we truly believe that containers and EC2 spot instances are made for each other. Containers are ephemeral by nature. They tend to be easy to drain. Kubernetes knows how to manage all the replicas, the failovers, the stability of your cluster, and the distribution of it. So because of that, Kubernetes handles spot instances very well. But we also want to be planning for those interruptions. There are some things we have to take into account before we go for it. So we need to remember that those instances will be preempted and taken away. There are different mechanisms to follow these things and to notice those interruptions. Your capacity will be affected. Instances will be pulled out, and also their state will be lost. When AWS takes away a spot instance, it takes the volumes, it destroys them, it takes the network interface and destroys it, and you spin up a new instance with new resources attached to it. And you have a pretty short period of time to handle that. Traditionally, AWS will give you 2 minutes. That being said, all these situations can be handled by understanding the markets, the regions, the instance capacity, handling those interruptions gracefully, making sure to drain our nodes and let Kubernetes move the pods over in time, making sure to spin up new resources before the old ones go away completely, and always keeping resources available in our cluster. And lastly, as I mentioned, so now we've done all this great job. We moved different instance types, we moved different instance sizes. We saved about 30% of the footprint of the cluster, simply run 75% of what we originally had. We took it and we put it on spot instances. We get a 60–90% discount, which is great. We're already saving about 85% of what we started with. But again, if every one of your developers is asking for 12 vCPUs for a 2 vCPU task or a pod, then you're paying 6 times of what you should. You save 90%, but that's still nothing in comparison to what you could be saving. And because of that, we also want to think about right sizing. You should be monitoring your pods roughly every 10 seconds for their utilization, getting a better understanding of your allocation, which is how Kubernetes is going to be scheduling them, versus how much the pods are actually using when they run. You want to make sure that these things are tightly coupled while addressing spikes and edge cases. With that, you want to update the resource requirements in every one of your deployments and how you're managing it, restart the pods and redeploy it, and making sure this is effectively being utilized. You'll probably, again, cool down a bit with those and perhaps dynamically respond to them in real time. What are the advantages of doing that for you as a company? So obviously cost, the greater efficiency that comes with it. You're paying only for what you use. You're not wasting any resources, and you're using optimized cost models. Productivity is improved. As I mentioned, when your data scientist needs to run a GPU, they can just go ahead and do that. They don't need to call your DevOps team, and you don't need every other developer pinging you every day, asking for new resources and new capabilities inside the cluster, but rather simply let them deploy those containers and let your infrastructure respond accordingly. And it will be very simple to scale because it's going to respond to the pods anyway, so you don't have to think about scaling policies anymore. You don't have to plan when you scale up and when you scale down. Simply tightly couple with the infrastructure and what it requires from an application layer. And that all sounds great. But how do you actually do that? So you can turn on millions of knobs and switches and do it by yourself and continue maintaining it for a while. Or it could go with SpotInstOcean. SpotInstOcean, which Ticketmaster will soon share the journey we've went through together, is our engine for serverless containers. It does automatically, basically with the click of a button, everything I just mentioned to your existing Kubernetes workloads. It will give you the container-driven auto-scaling by auto-detecting all your deployments, their tasks, and what they require, and spinning up the right instance at the right time. Everything happens as a SaaS layer inside your existing environments. It will simplify operations because you don't have to build this engine I just mentioned, and you'll simply be able to deploy and focus on differentiating work and what makes your business a great business. Ocean will work with any data plane management, so bring your own container orchestrator that can be ECS, Amazon EKS, any other type of Kubernetes of any flavor and shape, OpenShift, Rancher-backed, and Ocean will wrap around your worker nodes and make sure that everything is managed seamlessly. The container-driven infrastructure auto-scaling will make sure you always have the capacity you need. You'll never have any issues and need to go to manually release your cluster. But at the same time, it will maximize your resource utilization and make sure that the stuff you spin up are actually being used. As I mentioned, it will work with everything that you have today, and it will help you achieve about 90% cost optimization, while also helping you monitor the pods, get the cost showback that you need on those multi-tenant clusters. You have hundreds of developers, hundreds of applications. Who's spending what? Who's consuming how much? Has become a real black hole in Kubernetes clusters. And Ocean does that for you and shows you how much each deployment is using. And that's it for me. So with that, Tim?
Thanks, Tom.
Thank you, Tim.
I'm here tonight as rookie move. There we go. I'm here tonight to be the comic relief between the two geniuses over here. I'm going to give you guys a little bit of an update on what does Ticketmaster do. I think most people know the brand, but what does that translate to in technology, right? First, I'd like you all to take a moment and think back to your first big live event. Maybe it was an NFL game, maybe it was a big concert, I don't know. For me, it was AC/DC, 1986 Tacoma Dome. Blew my mind. Now, about 3 years ago, I took my son to his first live event, and at the time, he was this huge 21 Pilots fan. Folks here know who 21 Pilots is? Yeah, there you go. He would wander around the house singing Blurry Face until we all wanted our ears to be blurry. But we found him tickets. He was at the Sasquatch Festival. They were at the Sasquatch Festival, and I made the 4-hour drive from Seattle out to the gorge, which is where I took this picture. Beautiful setting. And his mind was blown. He got to see a bunch of other acts. He took it all in. And then on the 5-hour drive home, he was beaming and just chatterboxing. And if you can imagine how hard it is to get a 13-year-old boy to chatterbox, it's gold for a dad, right? So this is what Ticketmaster does. We create unforgettable moments of joy. That's the core of what it is that we deliver out to everyone as fans. And we do it at massive scale. We do $32 billion in GTV a year, 480 million tickets sold, 29 countries, 12,000 clients. Clients like the NFL, the NBA, MGM Resorts, Caesars, right here. So when we do this at scale, it's not always easy. This is what our network graphs look like multiple times a week. So to sell tickets at scale, Oftentimes what we have is maybe 50,000 seats, and then maybe 500,000 people that want those seats, and then maybe 5 million bots that want those seats before the 500,000 people can get them. So in a roughly 5-minute window, we have to identify the right people to sell those tickets to and deliver them so that the fans can go and get in and have that unforgettable moment of joy. Doing that at scale is hard, right? So I bring you back to this picture because when I think about our infrastructure that we use to deliver this, it's like the sea of people that you're looking out on this field on it. It's a lot. It's big, right? We have 27 ticketing systems, 250 plus unique products, 1,400 people, 15,000 network endpoints. And do we do Kubernetes? Absolutely. Over 1,000 nodes at baseline now that scales up on demand to easily double that. And Jesus will give us some more details there. And it's growing like wildfire inside the company. But then when you look at this picture again, the metaphor, think of the vast expanse of the Columbia River Gorge. So much bigger, it dwarfs the sea of people that's here, right? And that's the problem space that we work in. That's what we're trying to achieve with this scale. So we have to do it really efficiently. Even though we've got a lot of tech to work with, it's not enough unless we are really squeezed down to efficient, fast, useful resources. So about 7 years ago when I joined Ticketmaster, we were a big organization that had been around for a while, and our culture was pretty much looked like a 40-year-old tech company, right? There was a lot of operations, there was a lot of development time, and there was a lot of friction in between the two. And to deliver fast as a company at the time, we had to figure out a way to improve on that. Otherwise, the small companies that were nipping at our heels were going to take our business. So like many other people, we went DevOps. We jumped right into that bandwagon, and super effective, actually. Like in the last few years since we went to a DevOps channel, we have vastly accelerated what we've delivered. We've done things like fully digital ticketing in NFL. It's crazy. It's a complete flip on how ticketing works. But when you do something like DevOps, many of you probably have seen this, when you do DevOps, it's not just a walk in the park, right? You create some chaos. In fact, we created a lot of chaos. We learned a lot. We came out of it knowing some things that we had to fix. Number one, we had significantly diverse developer experience between autonomous teams. They were out kind of doing their own thing, trying to solve their problems because we'd given them autonomy. That meant they had different experiences. Suddenly, they had to figure out how to deliver in AWS. They went from having a systems engineering team who would just deploy their software for them to having to understand what's an EBS volume and what's an EC2 instance and what are all these instance types. Those teams would go out and they'd build because their focus is product delivery. They'd deliver on those products and sometimes not so much thinking about how do they deliver in an efficient way. And they would, they'd oversize instances, et cetera, because they had to guarantee that their product was up. And then lastly, when you go from a team that their 100% job is to deliver a highly available SIS service to now handing that core competency off to teams that their 100% job is to deliver features, you see a change in your operability, right? So we had to figure out how to solve for these things. And a few years ago, some colleagues and I went out to KubeCon just on a whim in Toronto. And Kubernetes was still really new. But immediately we figured out we need to bet on this technology because it checked all the boxes. And we did bet on it, and then the results came back. So now we're in our Kubernetes space, we're delivering a consistent developer experience between our data centers and on-prem. It's pretty cool. We've measured a 5x improvement in resource utilization between the Kubernetes space and the VM usage inside of Ticketmaster. And in our partnership with Spotinst, we've been able to deliver 60% cost reduction on the resources after that 5x improvement. So that's pretty huge. Additionally, that last thing about operability, well, Kubernetes has automated service recovery, right? So this ability for pods to repopulate when there's outages, that's actually what makes it possible for us to use Spotinst. We do 100% Spotinst in our Kubernetes clusters. Amazon reclaims, we just start them back up again. It's great. So, comic relief is almost over. We love Spotinst, absolutely. They've done fantastic stuff for us. Now what I want to do is hand it off to our principal architect in the Kubernetes space. He's going to tell you guys a little bit about the actual technology side of how we deliver Kubernetes and what that looks like for our developers. So, Jesus Carrillo, come on up.
Hey, thank you, Tim. Okay, before we continue, I want to set up some context here, and I need your participation. I want you to close your eyes and imagine the following. You are a developer, and you and your colleagues develop applications. You test those applications. You deploy the applications into production. And on top of that, you need to meet deadlines and manage the infrastructure that runs those applications. One day, one of your colleagues comes to your stand-up meeting and say, hey, I just learned that in the company, there is a set of engineers that are offering Kubernetes as a service. I think we should run our applications in Kubernetes. Everyone agrees, and now you can open your eyes. And let's take a look at the day in the life of a developer that, for the first time, is going to touch Kubernetes, and it's going to deploy its application quickly. What you need to do to onboard your application to Kubernetes. The first thing is create a namespace. That's a simple task. However, remember these clusters are multi-tenant, and there are a lot of other teams in the company using it. So you need to set up RBAC. Why you need RBAC? Well, you want to prevent other engineers in the company accessing resources in your namespace and doing tasks like killing a pod or listing secrets, stuff like that, right? Well, cool. And you need to authenticate the users and authorize them. At Ticketmaster, we use LDAP and Active Directory, so we tie RBAC policies back to LDAP groups. Next, network policies. Again, it's a multi-tenant cluster, and you want to prevent other systems running in the cluster to access your pods or resources. And also, you want to control what parts of the network your pods can talk. For example, if you have a public accessible application, you don't want those pods to be able to talk to an internal system or a database. Then, the next step is to come up with a deployment strategy. At Ticketmaster, we support Helm, plain Kubernetes manifest, and customize. But let's say you choose to use Helm. You will have to install Tiller. But since it's a multi-tenant cluster, multi-tenancy with Tiller comes with a few configurations, extra step. It's not just Helm init. And then we're a GitLab shop. And we encourage all our developers to deploy their applications from non-prod to production using CI/CD. you will want to install also a GitLab runner. And that sounds complex, right? Well, it's a lot of manifests you need to create, for sure. However, the Kubernetes, the team that manages those Kubernetes, has leveraged Kubernetes operators. And we have created an operator to create namespaces. We created a CRD that we called namespace configuration. You can see the spec in the screen. For example, we want the VIP group to be able, users from the VIP group to be able to access my awesome namespace. Also, I want Tiller installed, and I want a specific version of Tiller. Lastly, I am all CI/CD. I want a GitLab runner that is going to be associated with my super awesome team organization in GitLab. That means that only repositories that are part of that organization are able to deploy to that namespace. The next step is deploy your application. That's where the fun part starts. I think the Kubernetes provide a set of general purpose Helm charts. And let's say your application is a simple web service. So let's take a look how the workflow is. The first thing you need to do is create a GitLab repo under your organization. Next, create a Helm values file with super simple stuff like the container image you want, the host name you want for your ingress, and that's it. Then you sprinkle it with a little bit of GitLab CI, git add, git commit, git push, and as soon as you do that, the GitLab runner that is deployed in your namespace will pick the job. It will create an executor pod, and it will talk to Tiller or the Kubernetes API, depending on the deployment mechanism you choose. And then, after a few seconds, you end up with your application running in Kubernetes. This is super cool and simple, right? Well, it hasn't been like that. Let's time travel a little bit, and let's go to the version 1 of our platform. It was based off Tectonic 1.5. And when we roll out this platform, we had the time ticking on our backs. We didn't have enough time to plan it properly. However, we decided, we made a few compromises, and one of the compromises was, let's not take time to create the best network we can, and let's use one that is designed for other purpose, but let's use it. And we use one of our existing network topologies, which for other use cases work really well. However, for Kubernetes, it didn't work that well, because we had a huge network. We divided that network in logical segments, which called tiers. And each of these tiers had specific network ACLs attached to them. What we ended up doing is we created multiple autoscaling groups that will deploy EC2 instances on each of those networks. And we told the developers, use node selectors to schedule your pods into those networks. This worked well for the beginning. However, it has a lot of disadvantages. We couldn't provide autoscaling. The developer speed was reduced because if they need to scale and there wasn't enough compute power, they had to page us. And sometimes they forgot to use node selectors, stuff like that. And more importantly, it had a fixed instant type. But I think it's enough of the past. Let's go to the present. And right now, we are running the version 4 of our platform. This platform is based off a flat network. In fact, since platform version number 2, we did that. And right now, we are embracing a GitOps model. That means that whatever is in Git is whatever is deployed in the infrastructure and in the Kubernetes configuration. For managing the AWS resources, we use Terraform. And for managing the platform configuration, we use Argo CD, which syncs whatever is in Git to the Kubernetes API. We also started rolling our own Kubernetes distribution. It's multi-tenant from the beginning. It has autoscaling built in. And importantly, we use multiple instance sizes. If you're wondering about the footprint, this new platform runs about 10 production clusters and average on 150 nodes per cluster, and it bursts up to 250. let's talk about our spot instance integration. As we mentioned before, regardless the environment of the cluster, from production to non-prod, we use 100% spot instances for our worker nodes. The benefits from integrating with spot inst is, of course, cost reduction, but also we see a lot of value with the spotted cluster autoscaler because it understands the requirements of the application in terms of resources and launches the specific instances that are required to handle that workload. Let's take a look at how we deploy a Kubernetes cluster. In the image, we see a happy Kubernetes. It's happy because it's going to deploy a brand new cluster. The only thing he needs to do is create the Terraform value files, set up some flags, git add, git commit, git push. And as soon as that happens, we have a set of dedicated GitLab runners that its only purpose is to run Terraform code. After like 10 minutes later, you have a happier Kubernetes because its cluster is up and running and ready to go. The end result of this Terraform execution is something like this. An etcd cluster on on-demand instances, an auto-scaling group that manages the API server nodes, and then all the workloads and workers are running on Ocean. Let's talk about what the lessons learned on this 2.5, almost 3 years of running 100% on Spot. Take a look at that graph. And remember, this is a 100% Spot instances workers nodes. Try to think what's wrong with that. In case you are wondering, well, you're using just 2 instance types. That's true. That's the problem. What happens if we get an interruption on M4 extra large? We will lose about 500 nodes of our compute capacity instantly. We detected that in one of our clusters, and we talked to Spotinst about it. And they say, yeah, you need to change the cluster orientation from cost to balanced. So after that change, this is how a healthy 100% Spotinst cluster needs to look like. You have multiple instance types and not too much worker nodes on each of that instance types. That means that you can get an interruption on any of the families or instance types, and you will lose a tiny bit of your compute power. Important, you need to reduce the node lead time. Why this is important? Because this is a highly dynamic cluster, and capacity is getting added and removed every time. So if you lose compute power, you want that compute power to be added to the cluster as soon as possible. But also at the event of a scale up, you will also want that compute power ready as soon as possible. The applications that run in this kind of clusters need to properly handle evictions. Let's imagine a transactional application. It will detect that it's going to be evicted. It should either roll back the transaction or finish it as soon as possible and die gracefully. We have 2 minutes to do that. Then developers need to really think about anti-affinity rules to prevent and spread workloads between ACs and prevent that all of their pods are running on the same worker node. In the past, we had to tweak the headroom settings for the elastic groups to prevent node churn. But that's a thing of the past because with Ocean, it's all managed by us.
Thank you, Jesus, for this great overview. You guys are really building some awesome machinery over at your ops teams. And truly, after seeing a few hundred deployments on Kubernetes, I can say that this is one of the most impressive ones out there. So I actually have some questions for you and how things change over time. So how did you choose instance types and sizes when you first deployed your cluster? So you kind of were making a plan and you made some choice back then.
Yeah,
and how did it change today?
Yeah, when we roll out the version 1 of the platform, we had a clear understanding on which applications was going to run in the cluster. And they had a well-defined compute power requirements. It was Prometheus and two other workloads, I don't remember. But that's what led us to pick an instance size on that time. However, the platform gained popularity among Ticketmaster super quick. And we hit a point where we couldn't onboard more applications because they required different CPU and memory offerings. With Ocean, and in fact, when we rolled the second version, we started using elastic groups. And we stopped thinking about instance types. And we started thinking about what's the minimum amount of compute units that a worker node should have to be efficient, and what's the maximum amount that we are willing to have on a single cluster, on a single worker. That's how we did it.
Nice, that's very sophisticated. And as everyone can see, you simply choose some families, you choose some resource limitations, and you kind of let the automation take it from there. And you end up with a very heterogeneous clusters with some C38XLs, some R52XLs, M58XLs, and really everything in between, while everything stays extremely highly utilized. So I guess over time, how did this affect the kind of this heterogeneous cluster, the scaling of applications and infrastructures for both your developers that wanted some freedom, and to your operators, and how much bothering you get about it?
Yeah, I think from the developer side of things, they were able to stop thinking about instance sizes, and they used that amount of time and engineering to really understand their applications and how much compute power they require to be efficient. And from the operations side, we stopped thinking about instance types, and it's just how much compute power we want on a worker.
Nice. Yeah, as you can see, just a scaling event, checking what the resource requirements are, not thinking about a specific instance, how much CPU, how much memory is needed. Let's scale up what's the most efficient for that one. And we can see kind of a detailed overview of those events as well. I guess, so how did these heterogeneous clusters actually affect your resource utilization? Where were you in the beginning? Where are you today?
Yeah, when we were using elastic groups, it didn't have Bing packing. And with Ocean, we love the Bing packing because in the past, we had a bit of waste due to compute power fragmentation. But with the Bing packing that Ocean is providing, we are able to increase the efficiency of our cluster up to 80% of CPU and memory allocation, which is great.
Nice. And you mentioned about decreasing the node lead time. So you need your nodes to be kind of ephemeral, spin up faster when you work with spot instances. It's an important key aspect of it. What did you do over at Ticketmaster to reduce it from about the 15 minutes it was to the less than 4 it is today?
Yeah, well, when we were using Tectonic, it required the specific version of Docker to be able to function properly. And as we started upgrading Container Linux, the base operating system that it uses, the Docker version got upgraded too. So in the bootstrap cycle, it had to downgrade the Docker version, and it required 1 or 2 reboots. That added about 15 minutes. But now that we are in control of our Kubernetes distribution, we were able to tweak the bootstrap process, and it's about between 3 to 4 minutes.
Nice. So essentially, instead of letting the node boot up and then through the user data pull everything it needs, everything is baked into the images. Then when the nodes come up, everything is already there.
Right.
Nice. And how often do you find yourself updating those images?
We roll every time a new version of Container Linux is up, we upgrade it.
Nice. And how easy is it to kind of upgrade your workers afterwards?
Oh, that's super simple. We just run Terraform, and we do a cluster roll, and that's it. We just walk away.
Awesome. It's nice and smooth.
Yeah.
So Tim, I guess a question for you. So everyone here heard that Ticketmaster is running Kubernetes at a massive scale. Not all of it is in the cloud, and it's a shared tenant environment. You have over 1,000 developers in your organization. What does that mean for you from a cost governance standpoint, and how do you handle all of that?
Yeah, well, it's an excellent question, and it's one of my primary focuses is trying to drive cost governance in the cloud in general. For us, what we needed to do was come up with some sort of cost visibility model. So inside of Ticketmaster, we use our namespaces to connect back to product names and back to product owners, and then we drive that into a cost report. We worked early with SpotInst to actually produce some really great cost reporting spaces. Now, that was fantastic, and this data has been really useful. As we've grown into more hybrid cloud model and we've tried to demonstrate more cost modeling for the rest of our cloud, we've gone to a broader, more comprehensive report, but we still use this data that comes from SpotInst as our sort of backing and cross-check against that data. So it's been really fantastic.
Nice. That's a nicely sophisticated model. I see this to be a big challenge, and with a lot of customers running into containers and then figuring out that they're very blind to what's happening inside of them. So it's really
One of
beautiful
my
how you overcame
predecessors
that.
used to say that we, when we went DevOps, we gave all of our developers a machine gun loaded with Ticketmaster money and fired it at Amazon.
It's what a lot of companies do. Okay. Could you give a quick summary of kind of what were the benefits from going through this transition? So you mentioned 3 years ago you went to KubeCon. Are you happy with the choice you've made, and kind of what did you gain as an organization?
Yeah, absolutely. I mean, so the big thing has been accelerating development time, right? Ultimately, we have to stay ahead of our competitors, and so Kubernetes has been that. The cost optimization and operations overhead that we drive down associated with our partnership with you guys has helped to make that even more possible by making Kubernetes broader and more consumable. So it's been great.
That's awesome. Thank you very much, guys. So that's everything for me. If the audience has any questions, we're more than happy to take them. We still have 8 more minutes. So if anyone has any questions to Ticketmaster about the journey and the amazing platform they've built, or to SpotInst about how we manage infrastructure across our thousands of customers, we're more than happy to take them. And if not, we can get off stage.
And don't use the contact info on here. This is out of date. There will be a couple of people on Twitter that will not be very happy if you reach out to them. But we'll give you the real ones here. There you go.
There you go.
I have a microphone here too if anyone needs to ask them a question. I'm going to put the contact info up right here for you.
Oh, thanks.
There you go. That's the updated contact information. Anyone with a question?
So what percentage of utilization do you target? Do you go 100% memory, 100% CPU, or I'm surely you're keeping some in reserve for something. So what's the typical sort of target?
So how much buffer do we try to maintain in a cluster?
Mm-hmm.
So SpotInst uses dynamic headroom based on some machine learning models that track your deployments, utilization, and the sizes of the pods. They want to keep healthy units of work to be able to take every HPA movement or every small deployment instantaneously. So about 90% of the movements in your cluster will be instantaneous and simply have the infrastructure waiting for them. And then all these abnormal activities will simply have a single scaling event that scales up as many instances as necessary. And you can make it to be dynamic and autonomic, or you can make it manual in case you want some healthier, bigger buffers that match your use case better.
Right, and actually, I was just going to say the same thing. It's a tuning exercise, right? So it's kind of like having capacity planning in your team. You have to exercise that same regimen in each of your clusters, depending on how they're scaling. We were just having a conversation the other night about how we needed to make some tuning adjustments to the overhead that we wanted to have in some of our clusters. So.
Okay.
Yeah, so essentially, sometimes clusters get too efficient, and you want to watch out for that in case there is too much movement. There are hundreds of developers around them. Perhaps you need some healthier buffers around.
Hello. So how do you guys manage nodes moving from databases? So like for us, half of the costs are basically databases. And how do you manage them not getting out of sync? Like Cassandra, if you move like half of the nodes, then the cluster is not usable anymore.
Yeah, so I guess we can both share some experiences.
Yeah. we try not to run as much stateful applications as we will want in our Kubernetes AWS clusters. But we have a few really good use cases. For example, Kafka streams, that they analyze a massive amount of data, and they just use persistent volume claims, and they try to spread their workload across ACs. So and between worker nodes, so they kind of tolerate a few failures. That's how we are dealing with it right now.
Yeah. From the Spotting side, our autoscaler is aware of all the persistent volume claims and make sure to always maintain capacity and attach the volume to those nodes, so the Kubernetes scheduler can always keep the pod scheduled.
And just to add on to what Jesus said at the beginning of that, one of our original strategies with Kubernetes was to heavily focus on stateless workloads, because we have a ton of those. So we could do a lot of optimization in that span, learn how Kubernetes works, get our operations down pat, and then start moving into the persistence stateful workloads.
Could you guys talk about how Ocean reacts to the spot market? Like, is it enough information to react before an instance is taken from you, or is it always reactive?
Yeah, so essentially the core of the Spotting platform is a plethora of data on the different spot capacity pools and how they behave. And one of the things Ocean gives you is the ability to, as Jesus showed you, when you choose a balanced orientation, to make sure that your cluster is highly distributed while maintaining some buffers, while using the most highly available and least likely to interrupt spot capacity pools. And when an interruption is about to happen, we immediately preempt it by spinning up new resources in the other available capacity pools, or automatically falling back to on-demand instances if necessary, to always maintain the capacity and allow the scheduler to move the pods over or replace the replicas.
Yep. So I have a question for the Ticketmaster guys. So usually when you add new technology in the stack, there is a bit of an overhead that developers and operations need to learn that, probably do a proof of concept and test it until it actually goes to production. So I'm wondering, how long did it take for you guys to migrate from the original platform to the Spot-Inst or Ocean, and what's the learning curve? How steep it is?
Yeah, migrating from platform version 1 to 2 was kind of seamless, because Kubernetes abstracts everything. So at the end, regardless on the version of Kubernetes, you are talking Kubernetes. So migration was simple. From version 1 to 2, we had a little bit of learning curve, because we changed the way, like network topology, etc. But it was like 1 month, and we were able to migrate everything.
Yeah. We get, so in those migrations, it's really been an interesting experience inside the company, because most of the folks that are on Kubernetes, they're the early adopters, right? They're really trying to drive innovation in their space. But they're also, in many cases, tier 1 services. And so in the same conversations, a lot of times with them, they'll ask us for new features and the next version of Kubernetes, and then 10 minutes later they'll say, well, can you not do as many breaking changes? And it's it's a constant push and pull, but that just sort of is what it is when you're moving fast, right?
Thank you.
We have time for one more, if anyone.
Well, I hope this was helpful for you guys. Thanks for sticking around until 6:30 at night. These sessions are brutal.
Thank you, everyone.
Thank you, guys.